Welcome back to the third video in this series on an exercise in denotational design using affine functions as the denotation. So in the last video, we derived this definition for circle plus, which is an analogous operation for this one over here, which is addition on functions. And if you want to see the details of that, please go back and watch the previous video. In this particular video, we are going to be deriving an analogous structure to const q. Now, const q is the constant function that returns 0. So no matter what argument is given to it, it'll return 0. Of course, in the representation, the analogous type is a pair of rationals. And we don't know what this is going to be yet, so I'm just going to leave a hole here, and I've set up a derivation like this, and this here is a monoid homomorphism property, okay? And it's the monoid homomorphism property on the identity element of the monoid. Just to give you an idea, this here was the monoid homomorphism property for the addition operation. And it's fairly straightforward, given a particular mathematical structure, to come up with these homomorphism properties, because they'll be different for different mathematical structures. This is a monoid homomorphism because we're working with a monoid. Now, with that explanation out of the way, I think I'll start. So we're saying here that the meaning of 0AF is extensionally equivalent to const 0Q. This is an extensional equivalence proof, so we have to prove this for an arbitrary x value. So it's basically saying for all x, the meaning of 0f needs to be equivalent to const 0q. Well, the meaning of 0af applied to x is equivalent to const 0q applied to x. And as before, we're going to work forwards and backwards until we come up with a definition. So the first thing I'd like to do is work forwards. So I am going to just expand out what the meaning function applied to 0AF must be. Okay, so actually, we've got a bit of a problem here because I haven't really specified what the names of the components of the pair are going to be. So what I'm actually going to do up here is I'm going to refine this whole, and you can see that I'm going to need something for 2 and something for 3, and they should both be of type rational. Well, what I could do here is just say, well, where A, B both rationals, and A is a whole and B is a whole, then I could put A in here. I'll need to reload. I've made a mistake somewhere. Yes. My apologies, I'm going to remove that first. Reload, and I can put A in here. I can put B in here. Well, that's kind of nice. Okay. I just realized I've actually done the wrong thing here. So I'm going to put that back the way it was, because that's not actually going to help us at all. So what I'm going to do instead is I'm going to define what A and B are by using a let expression. I'm going to say in, and then I'm going to indent everything here by 2 spaces. And now I'm going to reload. Now A and B are in scope, and they're going to be the 2 components of AF, whatever they end up being. Okay, so now we can continue. And that should be true. Well, that's lovely. That's as far in the forward direction as I can go. Again, no, that's not true. I could do one more step. I can say that the meaning of A paired with B applied to X is A times X plus B. Reload that. That's all gone through. So like before, we're going to meet in the middle here. So now I'm going to work backwards from const 0q to the middle. So that's that. And we can say that we just substitute in the definition of const q. So we got that. And that all loaded. If you're unaware or new to Agda, I'm doing Control-C, Control-L in Emacs to reload the proof each time. And if there's any mistakes, it'll let me know. So, okay, how am I going to get this particular thing in some form which looks like A times X plus B? Well, I think it's going to be 0 times X plus 0. Okay, so I can just do one more simplification, which is that obviously the constant function applied to X is going to be 0, so that should be true as well. But at this point in time, 0q is just not equal to A times X plus B. That's just not true. So the first thing I'm going to do is I'm going to use the property. I'm going to introduce the whole first. I'm going to use the property that 0 is the right identity to say that the following is true. Actually, no. I'm going to use the property that 0 is the left multiplicative identity of X to say that the following is true. All right. So how might we do that? Well, what we can do is say we use this property times 0 L and we can refine on that, and then I'm going to require something here, and it's going to be X. Okay, so I've now shown that 0q times X is equal to 0. Well, that's nice. The next thing I want to do is put a hole in here, is say that 0q times X plus 0q is equivalent to 0q times X. And in this case, I am going to be relying on the property that 0q is the right additive identity. I am going to have to use a congruence rule here. Maybe I don't have to use a congruence rule here. Maybe it's simply a case of using plus identity R applied to 0q. Let's see if that works. So it's not liking that, and my error message is not particularly useful. I might just make it a bit smaller. What I really need to do is look at the definition of this. So what I might do is go have a quick look inside the Agda standard lib and look in data rational properties.agda, and I'll increase the size of that. I'm going to search for plus identity R, and that's right identity here, and then that here says for all x, x dot e is equivalent to x. Okay, so that is what I'm looking for. Oh yes, okay. So what I've done here is use the wrong expression here. Now that's lovely. Okay, so I've substituted in 0q star x as the first argument over here. And now I've got 0q star x plus the identity element, which is 0q, is equivalent to 0q star x. Okay, great. I'll just leave that window open there. So now I've got something that is actually in the right form, and I can fill in the definition. So it probably wasn't a huge surprise that this was going to be the definition for 0OF, but I fill in the definition, I remove the hole, I press C, Control C, Control L, and voila, we have done the derivation of 0OF. And that concludes the two operations / constants for this particular monoid. So in the next video, we'll be looking at the other monoid that affine functions are a member of, which is a monoid under function composition and the identity function. So I'll see you in the next video.